A very good morning to one and all present here. Today we will discuss the network synthesis topic, that is the synthesis of the driving point function. Now, what do you mean by the first we will discuss about the what is the driving point function? The driving point function are those functions which are measured at the same port. For example, if we have considered a one port network, the one port means there will be two terminals. Okay, and if we measure both the voltage and current at the same port, it is called as the driving port. So there are two quantities, one is a voltage, another is the current. So if we measure both at the same port, it is called as the driving point of quantities. So if we measure the impedance, so it is a ratio of the Laplace transform of the voltage to the Laplace transform of the current. So it is called as a driving point impedance function. Similarly, if we take the just reverse of the ratio, that is the Laplace transform of the current to the Laplace transform of the voltage, then it is called as a driving point admittance function. So basically, when we see that the driving point function, it means there are two functions. One is the impedance function, another is the admittance function. And we are doing the synthesis of the driving point function for one port network. Now we know that there are basically three passive components, that is the R, L and C. So what are the possible combination of the synthesis of the driving point function? They are the three combination. One is the RL, another is the RC, and third is the LC network. So we will discuss in this synthesis topic basically the two element synthesis, and they are the three combination. So first we will discuss the basically the LC network synthesis. So before synthesis of the LC networks, we will first discuss how we will identify if the given function will be the made up of or designed from the LC network. So what is the first property? Say that either it is the impedance function or the admittance function. So it will be the ratio of the odd to even or even to odd polynomials. It means if we have given the ZLCS or maybe the YLCS, which is the, for example, s square plus 1 into s square plus 9 upon s into s square plus 4. Okay, if we open this factor form, we get s to the power 4 plus 10s square plus 9 upon s cube plus 4s. So we will observe that the numerator, which is called as the ns is numerator polynomial and ds is the denominator polynomial. So basically ns is s to the power 4 plus 10s square plus 9. So it is the even polynomials, while the ds denominator polynomial is odd polynomial terms. So basically it is the ratio of the odd to even or even to odd polynomials. Okay, now what is the second point? Say that the poles and zeros are simple and they lie on the j omega axis. Now what do you mean by this? For example, in this case, no, what are the basically the zeros? Now basically they are the four zeros because the numerators, the location of the roots represent the zeros. Now how many zeros? They are the four, that is the plus minus j1 plus minus j3. Now how we can determine the zeros? Basically we will make equal to 0, that is the s square plus 1 equal to 0. So s square equals to minus 1. So what is the s? That is the plus minus j1. This is the way of the determining the zeros and the poles. Similarly, s square plus 9 equal to 0, we get the roots are the s plus minus j3. Similarly, there are the poles will be the s equals to 0 and plus minus j2. Okay. Now, if we draw these poles and zeros in the s-plane, now what will happen? This is the real axis and this is the imaginary axis. So, how many poles? There are the three poles. One pole is at the basically the origin. We know that the poles are represented by cross. So this is at the origin. Okay. Then this is the plus J2 and this is the minus J2. So there are three poles. Now how many zeros? There are the four zeros and the zeros are represented by the circle. So we will mark this is the 0 by circle, that is a plus J1, this is the minus J1, and similarly the plus J3 and the minus J3. So what is the basically second point say that the poles and zeros are simple. It means there should be no repeated poles and zeros on the j omega axis. They all are the non-repeated and they lie on the j omega axis. It means in case of the LC network synthesis, all the poles and zeros, they will be lie on the j omega axis. They will not lie on the real axis or at any other locations. Now come to the third point. The third point say that these poles and zeros are alternate on the j omega axis. It means, for example, in our this case, at the origin there is a pole, then there is a 0, pole, 0. Similarly, at the downward side, pole, 0, pole, 0. So this is the third property. Now, fourth property say that the highest and the lowest power of the numerator and the denominator, they must differ by unity. It means if we consider what is the highest power of the numerator, s to the power 4, what is the highest power of denominator, s to the power 3. So what is the difference will be 1. Similarly, what is the lowest power of the numerator, 0. What is the lowest power of the denominator, 1. So what is the difference? Again 1. So this condition should be also satisfied. And the last condition say that there should be either a 0 or pole at the origin and infinity. Now what do you mean by that? In our case, how many number of zeros? There are 4 zeros. How many number of poles? There are 3 poles. It means there is a one pole is located at the infinitive. Why? Because so that the number of the poles and zeros will be equal. So in our this case, basically there is a one pole at the origin and one pole at the infinity. So this is the condition is satisfied. Now these all are the properties of the LC network. Now there are two methods of the synthesis of the driving point function. The first method is called as the Foster networks or Foster form, and second method is called as the Caillou networks and Caillou forms. Now the Foster networks are further classified into two categories. One is called as the Foster first form and second is called the Foster second form, or first Foster form or second Foster form. Similarly, the Caillou networks is also divided into two parts. That is, one is called as the first Caillou form and second is called as the second Caillou form. Now, the Foster network is based on the partial fraction expansion method. It means, if you know the partial fraction expansion method, we can easily solve the Foster network. Similarly, the Caillou networks are based on the continued fraction expansion method. This method we have already discussed in case of the Hurwitz polynomial. After discussing the properties of the LC network, now we will discuss the numerical problem of the first Foster form and the second Foster form. For example, we are given an impedance function and we have to synthesize the ZS as the first Foster form. And in the question, we have assumed that we have not specified what is the nature of the network. It means we don't know if this network will be synthesized by the LC or RL or RC. So first of all, we have to check all the basically the properties of the LC network. If it is satisfied, so this network will be synthesized by the LC network, and the properties we have already discussed. Okay, so after discussing the property, how we will solve this by first Foster form. So basically the first Foster form is also called as an impedance form. That is a very important thing, or series network form. Series network form, because sometimes in the question we have also asked that if we have to determine the impedance form or series network form. In both the case we have to basically design the first Foster form. No, we have already know that the Foster networks are based on the partial fraction expansion method. Now, before applying the partial fraction expansion method, that is called as the partial fraction PFE, okay, that is the partial fraction expansion method. So we have to know that what are the necessary conditions for partial fraction expansion method. If it means if we are given the numerator polynomial and the denominator polynomial. So for applying the partial fraction expansion method, the highest power of the denominator should be greater than the numerator power. If this condition is satisfied, then we can apply the partial fraction expansion method. And if this condition is not satisfied, so we will first divide this numerator by denominator. For example, in our case, this ZS, when we will expand it, we get s to the power 4 plus 10s square plus 9 upon s cube plus 4s. So here the numerator power is greater than the denominator power. So basically directly we can't apply the partial fraction. So what we have to do? Basically we have to divide this numerator by this denominator one time. Now how? For example, mathematically when we divide the 7 by 2, so we can written in this manner, that is a 3 plus 1 by 2. Now what is a 2? 2 is called as a divisor. What is the 7? Dividend. What is the basically the 3? Question. What is the 1? Remainder. And 2 is again divisor. So similarly, we will write down this function is also in this form. So what we will do? Basically, we will divide this numerator s to the power 4 plus 10s square plus 9 by 1 times. Okay. Now, what is the first term? S to the power 4. What is the first term of this s cube? So we will invert them. What is the this become? 1 upon s cube. Now multiply this by s to the power 4. So what will be the question? S. Once you get this question, we will multiply this whole terms. We become the s to the power 4 plus 4s square. Change the sign. Now this becomes 6s square plus 9. So basically this ZS I can written in this similarly manner of the 7 by 2, that is 3 plus 1 by 2. Here the 3 is the basically or the question. So here our question is S plus what is the remainder? Here was the 1. Here is the 6s square plus 9 divide by divisor. What is this? That is the s cube plus a 4s. Okay. Now after dividing that, we will see that key in this polynomial ratio, the denominator power is greater than the numerator power. So we can't apply the partial fraction in this function. And we assume that this function is a suppose z dash s. So basically we will return this z dash s as a separately, that is the 6s square plus 9 upon s common and s square plus 4. Okay. Now after dividing this, we can apply the partial fraction in the z dash s. Now what is the basically the partial fraction expansion say that they are basically the 3 roots, or we can say they are 2 factors. Now this one factor, that is the s, is a simple, while another factor is a quadratic. We have already discussed, or we have already studied in the 11th class. For the simple factor, the partial coefficient will be a upon s, while for the quadratic factor, the partial coefficient is bs plus c. Okay. Now what is this? This is a z dash s. I will put the value of the function z dash s 6s square plus 9 upon s square plus 4. Now I will take the LCM. The LCM will be s into s square plus 4. Now, what will be the numerator become? S into s square plus 4 plus bs square plus cs. Now here is the same as it is the left hand side. Now both left hand side and right hand side are the same denominator. We will cancel out. Now we will open the bracket and take the common, that is a s square and bs square. What is the term become? A plus b s square plus cs, and this become 4e. Now after doing this, we will compare the coefficients on both the sides. So here, what is the coefficient of the s square? A plus b. What is the coefficient of here left hand side? 6. So what does this become? A plus b equals to 6. This is our first equation. Similarly, there is no term of the basically the s. So what is the c become? 0, and the last is a 4a equals to 9. Okay. So what is the value of a? A become 9 by 4. Substitute the value of a 9 by 4 into this equation number 1. So what is the b? B is a 6 minus a. So what is this become? 6 minus 9 by 4, which is become the 24 minus 9 by 4, which is a nothing but basically the 15 by 4. So once we know the value of the a and b, we will put in this value of the function the z-s. So what is the basically the z-s become the a is the our 9 by 4 upon s plus b is the 15 by 4 s plus c is 0 divided by s square plus 4. Now one important thing is we have to always remember that when we will apply the partial fraction, then this ds plus c, that is the basically the partial coefficient for the quadratic, this c will be always 0. Okay. Now, after applying the partial fraction expansion in z-s and substituting the value of a and b, now we will find out the value of the z-s, which is basically s plus the z-s. Okay. Now then we have to basically rearrange this function in this manner, that is a 1 upon the 4 upon 9s. So basically we have divided this numerator constant by 9 by 4, then plus, what is this numerator? Is a 15 by 4s. So we will divide this numerator term by each denominator and numerator. So what does this become? 1. Now what does the denominator become? The denominator become basically the 4 upon 15s plus 16 upon 15s. So basically we have divided. Okay. Now after that we will assume that they are basically the three sum of the terms. So basically this will be the z1s, this will be your z2s, and this will be z3s. Now we have already discussed in the positive real function that for inductor, what is the transform network is the SL. For capacitor, the transform network is a 1 upon SC. So basically, when in the numerator is a S, okay, in which denominator is a 1, so this will be always represent the inductor. While the second term Z2S, which is the 1 upon SC, so basically this term represent the capacitance. So they basically represent the single element. While in case of the here there are two terms of the S, it means this Z3S is the combination of the two element. One is inductor and another is the capacitor. It means when both are connected in parallel, so what will be the equivalent impedance? That is the Z1 Z2 upon Z1 plus Z2. What does this become? SL plus 1 upon SC. Okay, so what will be this become? This is our Z3S. So this is the, I will take the LCM. This is become S square LC plus 1. The SC and SC denominator is cancel out. Then we will divide the each term by the SL. So this become the SC plus 1 upon SL. Now then we will compare. Then we can and this equation. So we will found that this is the represent the 4 upon 15 capacitance value, and this is the 1 upon SL. So basically we will rearrange this equation also. So it become 15 upon 16. So this represent the inductor. So this is a way of the synthesizing the network. Now after identify the LNC, we will draw the network. We already know the first Foster form is the basically the series or impedance form. So first is the Z1S. What is the Z1S? It is a S. What is the coefficient of S? Is 1. So basically it is represent the 1 Henry inductor. Z2S is basically the 1 upon SC. So what is the second element represent the capacitor? What is the value? 4 upon 9 farad. So Z3S, which is the parallel combination of L and C, we have already discussed at the here. So this become the L and this become the C. Now what is the value of the L? That is a 15 upon 16 Henry. And what is the capacitance? That is a 4 upon 15 farad. And this is the impedance form. So basically, this is the way of that the synthesis of the first form net. So there is another method of the determining the partial friction expansion coefficients. So what is this method? Say that we have given the ZS find the partial coefficients. Now this we have already know that the after dividing the numerator by denominator we got the s plus 6s square plus 9 upon s into s square plus 4. Now I will return this is in this manner, that is the s. I will return this is the s plus j2 and s minus j2. So basically we convert this quadratic term into the simple factor form, that is there are two roots. One is s plus s equals to plus j2, another is s minus j2. So what are the factor form is this. Now after that we will assume this whole term as the ZSS. Then what is the ZSS? The ZSS become 6s square plus 9 upon s into s plus j2 s minus j2. Now here all the factors are the simple. So we will simple apply the residue method or partial fraction method. So what is the first is the k1 upon s plus k2 upon s plus j2 plus k3 upon s minus j2. Now in this method, because all the factors will be simple, so these all the coefficient will be simple, there will be no s terms. That is the plus point of this method. Now how we will determine these the coefficients? That is the k1. So what is the k1? The k1 is basically the factor of this coefficient of this factor s. So we will multiply this s by z dash s and putting s equals to 0. So what is the z dash s? This is this term. So when we will multiply by this s, so this s will be cancelled out. So what is the remaining become 6s square plus 9 upon s square plus 4. Now why I am written here s square plus 4? Because s plus j2 and s minus j2 is their product is already we know s square plus 4. Putting s tends to 0. So what does this become? 9 by 4. So this 9 by 4 is the same as we have earlier determined that was our A. So this A and this K1 both are the same thing. Similarly, we will determine the K2. Now what is the K2? The K2 is again same way. What is the factor? Is s plus j2 multiplied by z dash s and putting s equals to minus j2. Now how we will determine this? Equating to 0 s plus j2, we get s equals to minus j2. Now again when we will multiply by this, so this term will be cancelled out. So what is the term become? 6s square plus 9 upon s into s minus j2 and putting s equals to minus j2. We will put this value at the here. So 6 minus j2 whole square plus 9 upon minus j2 minus j2 minus j2. Now this is the minus ka whole square is a plus, but j square is a minus 1. So what does this term become? Minus 24 plus 9 upon this become minus j2 and this become minus j4. So when we will both multiply, so this is the numerator is minus 15. Now this become minus minus plus, but j square is also minus, so this become 8. So basically our K2 is 15 upon 8. Now once we know the K2, we did not require to find out the K3. Why? Because K3 is basically the conjugate of the K2. So what is the conjugate of the K2? This will be also same. Now once we know the K1, K2, K3, now we will find out the Z dash S. What is the Z dash S? Was the K1 upon S plus K2 upon S plus J2 plus K3 upon S minus J2. Put the value. What is the K1? K1 we have already determined earlier. That was the 9 by 4 S. K2 is the 15 upon 8. K3 is also 15 upon 8. In both the terms, the 15 upon 8 is common. So this becomes 9 by 4s plus 15 by 8 is common. Okay. Now s plus j2 and s minus j2, we will take the LCM. So what is the numerator become? S minus j2 plus s plus j2. Now this j2 and the j2 will be cancelled out, and this become the 2s. So this is a 9 by 4s plus 15 upon 8. Now this become the 2s upon s square plus 4. And this 2 will be cancelled out. So this become 15 by 4. So basically this 15 by 4 will be same as the earlier we have determined the partial coefficient B. So this is another way of the determining the partial fraction coefficient. Okay, in the last class we discussed about the first Foster form. Now today we will discuss about the second Foster form. Now again we have given the same impedance function, and we have to synthesize this impedance function as a second Foster form. Now before discussing that, we have to know that this second Foster form is called as the admittance form. That is one important thing. And this admittance form is also called as the parallel network form. It means, or synthesize this impedance function as a second Foster form, we have to first convert the given impedance function into admittance function. It means we have to first determine the admittance or given impedance function, which is a ys equals to 1 upon zs. So it becomes s into s square plus 4 into s square plus 1 into s square plus 9. Why we have inverted them? Because the given function is an impedance function. But suppose if the given function is an admittance function in place of the impedance, then we need not require to invert them, because function is already given in the admittance function. So these things you have to remember carefully. Okay, now come to our question. So our function is an impedance function, so we have inverted them. Now once we have inverted them, okay, so what is this? Denominator become s to the power 4 plus 10s square plus 9. So here the denominator power is greater than the numerator power, so we can directly apply the partial fraction method. Now in this partial fraction expansion method, we will, that is called as the PFE, we will apply the basically the residue method. So what is the residue method? We have already discussed. We will convert this quadratic factor form into the simple factor terms. Look like this, that is s into s square plus 4. So what is s square plus 1? Simple factor s plus j1, s minus j1. So basically we have to equating s square plus 1 equal to 0. So there will be two roots, plus j1 and minus j1. So we will return in the factored form. Similarly, the s square plus 9 is s plus j3, s minus j3. Now after doing this, all the factors are basically the simple. To apply the partial fraction method, so what does this become? K1 upon s plus j1 plus K2 upon s minus j1 plus K3 upon s plus j3 plus K4 upon s minus j3. Now one interesting point is that the K2, which is a factor coefficient of the s minus j1 factor, and s minus j1 is basically the conjugate of s plus j1. So basically we did not determine the K2 because K2 will be the K1 conjugate. Similarly, the K4 will be K3 conjugate. This is the advantage of this method. We have to only determine the K1 and the K3. Once we know the K1 and K3, we can determine the K2 and K4. Now how can we determine the K1? Multiply this s plus j1 factor by our function is the ys, which is on the left hand side, and putting the s equals to minus j1. Now when we will multiply by s plus j1, so this term will cancel out. So what is the remaining term become? S into s square plus 4 upon s minus j1. Now this is the, for simplicity I am writing s square plus 9 so that the calculation will become simple. Now I will put s equals to minus j1. So what is the basically the, so this become minus j1. Now this is the minus j1 square plus 4. Now denominator is the minus j1 and again here the minus j1 square plus 9. No, minus whole square is a plus 1 but j square is a minus 1. So what does this term become? Minus j1. Okay, and this become the minus 1 plus 4. Now divided by this become minus j2. And again this will become the minus 1 plus 9. Now this j minus j and minus j will cancel out. So what does this become? 1 by 2 into 3 by 8. So basically this becomes 3 upon 16. So we get the K1 is a 3 upon 60. So what will be the K2? The K2 will be also the 3 upon 60. Now similarly we will determine the K3 also. Now what is the K3? The K3 will be look like a S plus J3 multiplied by Ys and putting S equals to minus J3. Now again when we will multiply by S plus J3, so this J3 will cancel out. So what is the remaining become? S into S square plus 4 upon, for simplicity I am writing this become S square plus 1 and this become S minus J3. Now I will put the S equals to minus J3 in this equation. So minus J3, this was become minus J3 whole square plus 4. Now denominator become again minus J3 whole square plus 1. And this become minus j3 and minus j3, this is become minus j6. So what is this become? Now this become minus j3. Now this is the minus whole square is a plus 1, j square is a minus 1, so this become the basically or the minus 9 plus 4 and this is minus j6 and again minus 9 plus 1, minus j and minus j again cancel out. So what does this become? 3 into minus 5 and 6 into minus 8. So finally this is result is 15 upon the 48. Then we will simplify, this become 5 upon 16. Okay, once we know the K3, so what is the K4? This is also 5 upon 16. And once we know the value of the basically the K1, K2, K3, we will put the value of the K1 and K2 at the here. So what is the K1? The K1 is our 3 upon 16. What is the K2? Also 3 upon 16. What is the K3? That is a 5 upon 16. What is the K4? Also 5 upon 16. So now after calculating the K1, K2, K3 and K4, we will substitute into this expression. Now again here the 3 upon 16 is common. What does this become? S plus J1, S minus J1. We have taken the LCM. Now what is the numerator become? S minus J1 plus S plus J1. Similarly same for at the here. This become 5 upon 16. Okay, now what does this become? S plus J3, S minus J3. Okay, now what does this become? S minus J3 plus S plus J3. Now what does this minus J3 cancel out? This is also cancel out. So what does this become? 3 upon 16. It become 2s upon s square plus 1. This become 5 upon 16. And this become 2s upon s square plus 9. Now 2 will be cancelled. So what does this become? 3 upon 8s upon s square plus 1 and 5 upon 8s s square plus 9. Okay, now after again that we will divide this numerator by each term, both the numerator and denominator similarly. So what does this become? The numerator become 1 and in the denominator when we will return this is the 8s upon 3 plus it is become the basically our the 8 upon 3s. Similarly we will divide the this term. So 1 upon this become 8s upon 5 plus 72 upon 5s. Okay. Now here the ys is a basically this. So there is a no single term. It means there will be no single element. Here there is a basically the two terms. So it means this is the written as the y1s plus y2s. Now here y1s is also the combination of LC network and y2s is also combination of the LC network. Now before synthesizing the network, we will first determine basically what is the admittance of the SL. For example, admittance of the inductor is 1 upon SL. Similarly, what is the admittance of the capacitor is the SC, because it is just reverse of the impedance. Now, when two admittances are connected in series, okay, it means we have given an inductor and we have given the capacitor. And both admittance, that is 1 upon SL and the SC, when they are connected in the series, so what is the equivalent impedance? The equivalent impedance will be the product of them divided by sum. Why? Because they are admittance, and in the admittance the formula is the just reverse of that, of the impedance. So what does this become? 1 upon SL multiplied by SC, 1 upon SL plus SC. Take the LCM. What does this become? SC 1 plus S square LC. Now again divide by this SC. What does this become? 1 upon SC plus SL. So we will compare basically this term to the our y1s and y2s. So basically, what is this 8 by 3? Here it is the represent the inductance. Similarly, we will return this 8 by 3 as a 3 by 8 and 1 upon this. So this 3 by 8 is the capacitance. And similarly, this 72 by 5s I will return in this manner, 5 upon 72. So this 5 upon 72 is the capacitor. So final what will be the network? The network is look like that. It is basically the 1L and the 1C. This is for y1s, and another is the y2, which is another inductor and the capacitor. Because there is no single term, so both the LC network will be the series branch, and then it is also series branch, and then result is connected in parallel. So that's why it is called as the admittance form or the parallel network form, and each term should represent the admittance, and this will be your the equivalent admittance. Now, what is the value of this inductor? The inductor value is 8 by 3 Henry. What is the value of the capacitor? That is a 3 by 8 Farad. Similarly here, this is the 8 by 5 Henry. And this is the our 5 upon 72 Farad. So this is the complete of the basically the synthesis of the first Foster form and the second Foster form for the LC network. Thank you everyone.